Welcome back to students. Welcome back. So in this video we are going to solve the more problems in the first unit of gas dynamics and jet propulsion. First problem, air flow through a duct with a velocity 300 meter per second, pressure 1 bar, temperature 30 degrees Celsius. Find first one, stagnation pressure and temperature. Second one, velocity of sound in dynamic and stagnation condition. We know that velocity of sound at the entry condition C1 equal to root of gamma RT is equal to 20.05 root of 303. Then C1 is equal to 349 meter per second. We know that Mach number is equal to V by C and is equal to 300 divided by 349. Here velocity V1 equal to 300 meter per second, it is a given data. Therefore find out the M1 equal to 0.86. Then stagnation properties P0 and T0 from the table, gas table. Here T1 divided by T0 at Mach number is equal to 0.86, then is equal to 0.871. Therefore T0 equal to 300 divided by 0.871. Finally, T0 equal to 347.9 Kelvin. Then find out the P1 divided by P0 at Mach number 0.86 from the given gas table is equal to 0.617. Then find out the P0. P0 equal to P1 divided by 0.617. Then finally P0 equal to 1.62. And we know that velocity of sound at a stagnation temperature C0. Here C0 equal to root of gamma RT or KRT, and finally find out the C0 equal to 373.97 meter per second. Here it is a second question in this video. Air at a stagnation condition has a temperature of 700 Kelvin. Find the maximum possible velocity. What would be the sonic velocity if the flow velocity is 1 by 2 of the maximum velocity? Here we know h plus v square divided by 2 is equal to h naught. V square divided by 2 is equal to h naught minus h is equal to Cp T naught minus T. Here V becomes maximum when T equal to 0. V square maximum divided by 2 is equal to Cp T naught is equal to 1005 into 700 into for joule per kg Kelvin into Kelvin. Therefore maximum velocity is equal to root of 2 into 1005 into 700 is equal to 1186.2 meter per second. Maximum possible velocity is equal to obtained is equal to 1186.2 meter per second. And next find out the new flow velocity. V1 is equal to V max divided by 2. Therefore 1186.2 divided by 2 is equal to 593.1 meter per second. We have h1 plus v1 square divided by 2 is equal to h naught. Then Cpt1 plus 593.1 square divided by 2 whole square divided by 2 is equal to Cpd naught. Then T1 plus 593.1 whole square divided by 1005 into 2 is equal to T naught. Therefore T1 plus 700 minus 593.1, T1 is equal to 700 minus 593.1 whole square divided by 2010. Therefore finally T1 equal to 524.99 Kelvin, approximately 525 Kelvin. Next one, find out the sonic velocity. C1 is equal to root of KRT is equal to 20.05 root of 525. Then finally find out the C1 equal to 459.4 meter per second. So next question is, air is discharged into atmosphere from a big vessel through a nozzle. The atmospheric pressure and temperature are 1.1 10 power 5 Newton per meter square and 40 degrees Celsius, and the jet velocity is 100 meter per second. Find the chamber pressure and the temperature. We know that Mach number M1 equal to V1 divided by C1 and C1 equal to root of gamma or T1. Therefore, C1 equal to 354.2.72 meter per second. Then find out the M1. We know that M1 equal to V1 divided by C1 and V1 equal to 100. It is a given data. Therefore, M1 equal to 0.28. It is a less than 1, less than 0.1. This is subsonic Mach number, subsonic velocity. Therefore, then find out the stagnation properties P0, T0. From gas table, we have P1 divided by P0 at Mach number M equal to 0.28. The data, the obtained data is equal to 0.999. Therefore, P0 equal to P1 divided by 0.999 is equal to 1.1 into 10 power 5 Newton per meter square divided by 0.999. Therefore, P0 equal to 1.101 into 10 power 5 Newton per meter square. Then find out the T1 divided by P0 at Mach number M equal to 0.28 is equal to 0.999. Therefore, T0 is equal to T1 divided by 0.999 is equal to 313. It is a given value. So finally find out the chamber temperature T0 equal to 313.33 Kelvin. So next problem. Air is stored in a big container at temperature 400 Kelvin is allowed to expand adiabatically through a pipe. Air at station A downstream in the pipeline, the air attains a velocity of 250 meter per second. Find velocity of sound in the container and at station A in the pipes. Answer. Assumption: friction losses are neglected. We have from steady flow energy equation H plus V square divided by 2 is equal to H naught. CPT1 V square divided plus V square divided by 2 is equal to CPT naught. CPA TA plus V square A divided by 2 is equal to CPT naught. Then TA equal to 368.9 Kelvin. So the obtained temperature at section A is equal to 368.9 Kelvin. Next one, velocity of sound at the section at the station A is given by root of gamma or TA. Then finally find out the CA is equal to 385.1 meter per second. We know that Mach number at section A is equal to VA divided by CA. Here VA equal to 250 and CA equal to 385.1 meter per second. Therefore find out, so MA equal to 0.65. Finally find out the temperature in the chamber from gas table TA divided by T0 at Mach number 0.68. We find the answer 0.915. Therefore, from this equation, find out the T0 is equal to TA divided by 0.915. Then TA equal to 368.9. So finally, T0 equal to 403.17 Kelvin. So finally, find out the velocity of sound in the container C0. We know that C0 equal to root of gamma or T0. So we the 20.05 root of 403.1 Kelvin. It is a T0 value. Then finally find out the chamber velocity of sound in container C0 equal to 402.6 meter per second. So these are the problem in the first unit. The next topic, flow through nozzles. A nozzle is a duct that increases the velocity of flowing fluid at the expense of pressure drop. A duct which decreases the velocity of a fluid and causes a corresponding increase in pressure is a diffuser. The same duct may be either a nozzle or a diffuser depending upon the end condition across it. If the cross section of a duct decreases gradually from inlet to exit, the duct is said to be convergent. Conversely, if the cross section increases gradually from inlet to the exit, the duct is said to be divergent. Cross section initially decreases and then increases. The duct is called convergent, divergent nozzle or series nozzle. The minimum cross section of such duct is known as throat. Minimum cross section of a duct is known as throat. A fluid is said to be compressible if its density changes with the changes in pressure brought about by the flow. If the density does not changes or changes very little, the fluid is said to be incompressible. Usually, the gases and vapors are compressible, whereas liquids are incompressible. Here, the given figure, so it is a convergent nozzle. The first law reduces to Kh 2 plus V2 square divided by 2 is equal to Kh entry, the Kh final, Hf plus Vf square 2 or V square minus Vf square is equal to 2 into Hf minus He. If the inlet velocity is negligible, that is Ve equal to 0, then Ve root of 2 into Hf minus He, Ve equal to, the final velocity is negligible, then Ve root of 2 into Hf minus He plus Vf square. Velocity is increased at the cost of the drop in enthalpy. If an ideal gas is flowing through the nozzle, the exit velocity Ve can be expressed in terms of the inlet and outlet pressure and temperature by making use of the relation PV equal to RT or rho dH equal to Cp dt. Therefore, V square is equal to 2 Cp Ta minus Te is equal to 2 Cp Ta into 1 minus Te divided by Ta. From the relation governing the adiabatic expansion, we get the final equation. So next topic, diffuser. A diffuser can be thought of as a nozzle in which the direction of the flow is reversed. Although nozzle and diffuser is entirely different. So for an adiabatic diffuser, Q and WS are 0, work are 0, and the first law reduces. The diffuser discharges fluid with a higher enthalpy. The velocity of the fluid is reduced. Example of a reversible process. Slow compression of air in a balloon does not work on the air inside the balloon and take away energy from the surrounding. When the balloon is allowed to expand, the air inside and the surrounding air are both restored to original condition. Example of an irreversible process. Heat flow from hot to cold, never in the opposite direction. Most conductive and viscous processes are irreversible. Stagnation point is thus when the fluid is brought to a stagnant state. Example, reservoir. Stagnation properties can be obtained at any point in a flow field if the fluid at that point were decelerated from local conditions to zero velocity flowing and isentropic. Frictionless or adiabatic process. Pressure P0, temperature T0, density ρ0. If a fluid were brought to a complete stop, that is C2 equal to 0, therefore H0 represents the enthalpy of a fluid when it is brought to rest adiabatically. During a stagnation process, kinetic energy is converted to enthalpy. Properties at this point are called stagnation properties, which are identified by subscript 0. The process is also reversible. The stagnation state is called the isentropic stagnation state. Stagnation enthalpy is the same for isentropic and actual stagnation state. So it is a given diagram, x-axis and y-axis enthalpy, isentropic stagnation state, actual stagnation state, actual state. So actual stagnation pressure P0 act is lower than P0 due to increase in entropy S as a result of fluid friction. Now, nonetheless, stagnation processes are often approximately to be isentropic, and isentropic properties are referred to as stagnation properties. So next one we are going to solve the problems. The problem is a conical diffuser has entry diameter 20 cm. The Mach number, temperature and pressure are 0.6, 120 kN per meter square, and 340 Kelvin. The Mach number at the exits is 0.2. For one-dimensional isentropic flow, calculate the following: pressure, temperature, velocity at exit, mass flow rate at exit diameter, change in impulse function, changes in impulse function. So from the gas table, T1 divided by T0 at Mach number is equal to 0.6. Therefore is equal to 0.933. So therefore T0 equal to 340 divided by 0.933 is equal to 364.4 Kelvin. Therefore stagnation temperature T0 364 Kelvin. Then P1 divided by P0 at the Mach number 0.6 equal to 0.784. It is obtained from the gas table. Then P0 equal to 1.2 into 10 power 5 divided by 0.784. Therefore P0 equal to 1.53 bar or 10 power 5 Newton per meter square. To find the temperature at exit, we have T2 divided by T0 at the Mach number 0.2 is equal to 0.992. Therefore T2 equal to 364.4 into 0.992. Therefore T2 equal to 361.5 Kelvin. To find the pressure at the exits, we have P2 divided by P0 at Mach number is equal to 0.2 is equal to 0.973. Therefore P2 equal to 1.53 into 10 power 3 into 0.973. Therefore P2 equal to 1.48 bar. To find the velocity at the exit, sonic velocity at 1, therefore C2 equal to root of k RT or gamma RT equal to 20.05 root of 361.5. Therefore C2 equal to 381.2 meter per second. Velocity V2 equal to m2 into C2. Therefore velocity V2 equal to 0.2 into 381. Therefore V2 equal to 76.2 meter per second. Finally, to find mass flow rate, velocity at the inlet V1 equal to C1 into M1. Then is equal to root of KRT or gamma RT into M1. We have A2 divided by A star at Mach number 0.2 is equal to 2.914 from the gas table. Then A1 divided by A star is equal to at Mach number 0.6 equal to 1.188. It is also got from the gas table. Therefore A2 divided by A1 is equal to 2.964 divided by 1.188 is equal to D2 square divided by T1 square. Then A2 by A1 equal to 20.05 into 340 into 0.6. Therefore V1 equal to 221.82 meter per second. Then PV equal to MRT1, that is R1 equal to R1 or V1 equal to P1 divided by R1 is equal to 1.2 into 10 power 5 Newton per meter square divided by 287 into 340. Therefore V1 equal to 1.23 kilogram per meter cube or meter cube per kg. This is a specific volume. Therefore mass flow rate equal to rho. It is a density kilogram per meter cube. Rho AV. Therefore m dot equal to rho 1 A V1. Therefore m dot equal to mass flow rate is equal to 1.23 by 4 d square. It is a diameter equal to 0.2. So 0.2 whole square into 221.82. It is a velocity V1. Therefore m dot equal to 8.57 kilogram per second, kg per second. Impulse function, we know that impulse function F equal to PA plus rho AV square is equal to PA plus 1 plus rho divided by PV square is equal to PA into 1 plus 1 divided by RTPV square is equal to PA 1 plus KV square divided by KRT. That is F equal to PA 1 plus KM square. That is DF is equal to F2 minus F1. Therefore DF equal to impulse function the P1 A1 1 plus K M1 square minus P2 A2 1 plus K M2 square. Therefore impulse function DF equal to 6.53 kilonewton. So it is a fourth video. The next video is finally video. Thank you.